So this is essentially what you'd find in your textbook. I'm being a little bit more conceptual than perfectly conventional in the statement, but this is what he observed. Changing magnetic flux means an induced voltage. All right, so let's first revisit magnetic flux. So we talked about this with Gauss, and it would be the integral of the dot product of the magnetic field and differential area pieces, all right? And what Faraday noticed was that induced voltage, which often we write with this funny looking E, okay? All right, induced voltage will be the opposite, the negative, of the time rate of change of the magnetic flux. But this induced EMF is actually the summation of the electric field around the loop, and so it's actually the surface integral of the electric field along the length of the conductor is equal to this changing magnetic flux. Okay? So this is kind of pulling together some stuff we did prior to where we're going to take this next. All right? So, and then we're going to come back to this thing when we do electromagnetic waves or when we do Maxwell's equations, because this is a critical part. Faraday's law is one of the Maxwell equations. And basically, a changing electric field would produce a changing magnetic field, which produces a changing electric field, which produces a changing it just keeps going back and forth. And that's light. That's electromagnetic waves, which light is an electromagnetic wave. And it's just these oscillating electric and magnetic fields that are transverse, perpendicular to one another, oscillating through space in phase with one another. All right, so we'll come back to that, but we'll kind of goof around in this area a little bit. Now, let's just pay attention to this induced voltage piece of the puzzle. Minus d phi of the magnetic field, that's a capital Phi Greek letter. That would be the time derivative of AB cosine theta. Now, where do I get that from? From the dot product. Okay? We went over this with Gauss' law, so I'm expecting that you'll remember from Gauss' law. If not, go back and look at that again. So the flux equation, the integral of B to A will be AB cosine theta. Dot product's always cosine, cross product's always sine. Magnitude of the two things being multiplied times the sine, or cosine in this case, between them since it's a dot product. All right? So this requires that we do the product rule. So what we're going to get out of this is if I take this derivative, by the way it's negative, I forgot to put that negative there, I'm going to have A cosine theta dB dt minus B cosine theta dA dt plus, because of the derivative of cosine being a minus, AB sine theta d theta dt. Now that's just procedural obedience to the product rule, and that's great, and you should be able to do that in your sleep. I am not going to address that at all. What I'm going to address is why that is conceptually satisfying. All right? So this term right here, okay, this is where area and angle, meaning what is the inclination of your loop to the flux field, to the magnetic field, okay, are constant in this one. The magnetic field and the inclination of the loop to that field are constant in this one. And the area of the loop and the field remain constant in this one. Since there are three things that are material to the flux, the area for the flux to go through, the strength of the field, meaning or how much flux is going through any said area, and then the angle that that area is relative to the field. Those are all things that change, that influence the flux. And so I would expect, even if I didn't know what the product rule is, if I didn't have that procedural knowledge, I would expect that if the area and the angle are not changing, then A cosine theta would remain constant. But the magnetic field would be changing. And there's a zillion ways that we could have just arbitrarily picked to symbolize the changing magnetic field. We borrowed the one from calculus that used the differential, dB dt. And then in the next one, if I hold the other two things constant and let area change, then those things remain constant, and it's dA dt. And then in the last one, now those two should be really straightforward, especially given your calculus skill. The last one is less straightforward because a lot of people forget that the sine is the slope of the cosine function. Well, in this case, it's the negative. Okay? So if you were to plot a sine and a cosine function, and if you could trace them at the same time, you would notice that as you move them, the y value on the sine function is always the value of the slope of the cosine function, the tangent to the cosine. All right? So sine over cosine's tangent. So there's all those things there. But we forget about that because we think about sine, cosine, tangent. We're really usually thinking about triangles. That's our flinch reaction to it. And so, but the angle is changing. So if you're making the angle change, you have to have it be d theta dt. But since that function involves that angle, you've got to account for its change. And sine is the change of cosine, or the minus of it is. Okay? And cosine's a change of sine, et cetera, et cetera. And so that last one is harder to conceptually work out. Of course, the calculus of it makes it easy, just obey the rule. But why does that rule make any sense at all? And so Faraday's law is a context in which you can sort of make sense of the product rule. Because you need to account for all the permutations of change within this system. And the most comprehensive accounting for change would be hold everything constant but one thing. And then hold that constant in the next one and let something else change. And then keep doing that until you've let everything change by itself while the other things remain constant. And so if you have three things, there's only three ways to do that, which means I must have three terms that account for the change in this system. So what I've just told you is more important than the calculus. The reason it's more important than calculus is as scientists and engineers, you should know what to expect from your mathematics before you do the mathematics. Okay? You should expect that. All right? So what this means is if you only have one thing changing in the system, then you only have one term for your induced voltage. So if you hold two things constant and let the other thing change, then your induced voltage equation only has one of these terms. If you let two things change, then your induced voltage equation will have two non-zero terms. And if you let all three things change, the area of the loop, and it's how much area of the loop is in the field. Because the loop area usually won't change. I mean, it's a fixed thing. Okay? I mean, you can make a loop that does change, that its area does change. Okay? But what we're talking about is usually how much of that loop's area is still in the field. That's usually what we're talking about. All right? If you let all three things change, then you have all three terms. Simple enough, okay? So, all right. So that sort of does this. Oh, by the way, I guess we could write this, since this is really just omega, angular speed. So if we wanted to, we could write this as plus omega AB sine theta, because this is angular speed, angular frequency. All right. So if we wanted to have a expanded version of Faraday's law, it would be, the final form would be what I highlighted there. Minus A cosine theta dB dt minus B cosine theta dA dt plus omega AB sine theta. That would be the full bore equation that would account for every change possible. And so from a standpoint of, if you were accounting for this in some control system, as long as you have your magnetic field strength inputs what would you need in the code? You would need to know the area, you would need to know the magnetic field strength, you would need the angle of inclination, and you need every one of those coordinated in time. You need 4 pieces of information going into the computation in your control system. It's easy math, and sensors will tell us all this, and if the area is fixed and the angles is fixed, then you don't even have to, you just put the number in place. All right? But if they're not fixed, then you need a way to account for their not fixedness, so to speak. All right? So that's the big picture of Faraday's law. So let's use that knowledge on something. So get the recording going here. So 600 milliamps goes through this solenoid, produces a magnetic field. We expect this because it's an electromagnet. We given that time function for current, and then the coil, here's the data on this coil. It's got 3.4 centimeter radius. We're going to need that for the area, because we're stacking up 200 coil areas. It's not just one coil area. This is the area per loop. That's what's not obvious. I don't even think that's really obvious in the reading. I mean, they'll say it, but it's subtle. We keep talking about a loop area, but the law applies to a single loop. But if I have multiple loops, then I have to multiply it by that count. All right, so that's what we're headed at. So we're going to need all of this stuff as we move forward. So the circuit, would be something like this. Here's a coil. I'm not going to draw 200 windings, okay? And so area and theta are constant in this case. Therefore, that means my induced voltage is going to be that first term, A cosine theta dB dt. So it's just a really simple example of why it mattered to expand Faraday's law or the induced voltage out using the product rule. Okay? But you could conceptually go, well, I know that flux is AB cosine theta, and since I'm not changing A or theta, it's just going to be A cosine theta and the time rate of change of the field. You could just conceptually write that equation. But think about what's going on there. You understand the physics and you understand the calculus. That's usually not something that happens at the undergraduate level. Okay? Undergraduate level is a setup for a chance to obtain fuller understanding at the graduate and higher level. That's the reality for most of us. There are some weird people among us who manage to understand it fully now. And if you reveal who you are, we will beat you up after class, because that's not fair. It's not right. All right, I'm just kidding. Most of us have to struggle with it. I did. Anybody else with me? You wrestle with it, and you wrestle with it, and then one day you're like, gosh, I could have been so stupid. You know, when you have your aha moment, all right? And that began to happen for me as a senior. Persisted all the way through grad school, and it still happens. All right, that's the fun of learning. Anyways, meanwhile, back at the ranch. So what do we got to do first? Number one, we need to compute the area. Okay, and that's going to be, well, we know the area of one coil is pi r squared, but I have 200 of them. Okay, so that means that I'm going to have 200 pi times, what is it, 0.034 meters. Got to be in meters, can't do centimeters. Remember, everything's got to be in meters, seconds, etc. And so we're going to get 0.73 square meters for the loop area. So if you could cut each one of these 200 windings out and lay them out, they would be about 3/4 of a meter stick by 3/4 of whatever 0.73 square meters is. Roughly 3/4 of a square meter. Since the flux is going through all 200 of those loops, I have to multiply it by the number of loops that I have. More loops, more flux, because it's flux per loop, if you will. And every loop, as we saw in the simulation, gets more current flowing. More bang for the buck, if you will. All right? So we have one piece of the puzzle. Yay. Then, two, we need to recall that the magnetic field of a solenoid, so we would have briefly addressed this in the magnetics lecture, but so the magnetic permeability of free space. Little n is the number of loops per unit length. Okay, which we don't know how long this coil is, and that's fine. It doesn't matter. This is where we begin to cheat. Here is the mathematical sorcery, the witchcraft that we're about to practice, but it's the good witch of the north, or whatever that was in Wizard of Oz, okay? The east, whatever it was. And times the current. By the way, this is going to be the initial magnetic field, which we know to be 0.025 Tesla. Tesla is this weird unit for a magnetic field, okay? Now, we know, okay, given that magnetic field and current flow are proportional to one another, they are directly proportional to one another in an indirect way. All right? Meaning the amount of magnetic flux that's changing directly influences the amount of current that gets flowing. Current flows and thus sets up a voltage. So it's induced voltage by means of current happening for a different reason than normal. So we know that from all what we've seen in the simulations, what we've read about Faraday, and what I've parroted about Faraday, these have to be directly proportional to one another. And what this lets me do, and admittedly, this will seem like witchcraft, at least partially, is my time-dependent function for the magnetic field will depend on where the magnetic field starts. And since it's directly proportional to the current, and I have this time-dependent function for current, I'm just going to put that time-dependent function for current as my multiplier. Why did we do this? Two reasons. We did it, one, because we can. Two, I desperately need a time-dependent function for the magnetic field so that I can take its derivative. The mu naught Ni isn't a time-dependent function. Unless well, it is in that current always involves time, but I would need what is the structure of that time dependency. I must have that. And if I'm not given it, I must figure out what it is by some means.
So where did you get the current as a function of time? Assuming.
We do not discuss that. We do not discuss that. So it's just, that's a given, assuming that we have that function, okay, which either you do or you don't, but you can get it, all right? Walmart has them all the time. I'm just kidding. Didn't want to labor everything in the lecture. So now I can do a cosine theta dB dt because now I have a function for b that I can differentiate. And so step 3 here, this will be negative a cosine theta, and we'll have ddt of b naught 1 plus 2.4 inverse seconds t squared. And you go through all of these motions and you will come up with minus ab cosine theta, and we're going to have 4.8 inverse seconds t. So I'll spare you the calculus on that. And that will let me come up with the function for induced voltage as a function. This gives me a time function for voltage. Will be negative 0.088 volts per second times t. And so the E of 2 will give me a negative 0.018 volts. So at 2 seconds, which is what the question asked, what will be the induced voltage in the coil when t is 2 seconds? 2 seconds later. Okay? And that's what it's going to be, 0.18 volts. And if I know the voltage in this coil, then if I know coils have an inductance, and we'll get to that later, then I can start doing circuit analysis. All right, I know how much of the overall voltage this thing's going to chew up. Okay, but this is the induced voltage in this problem. So it's just really just what would I use? How could I use the expansion of Faraday's law? That's all I'm after here. All right, and all it requires is basic calculus, some arithmetic, some little bit of geometry knowledge, and then that step 2 thing. That's proportional reasoning. Okay? So that's a skill that usually is also takes a lot longer to develop than it should, but it does, just the way it is. These are things you need to know. Patterns you need to expect. methods that you need to learn how to deploy over the long haul, okay? So that your future professors and bosses don't look at you and make faces and laugh and stuff like that. All right. So if we have, I'm going to do my best to have a 3D So here's these two cube magnets. All right. I don't think that helped. All right. And if there's this wire loop, this rectangular wire loop, okay, and the width of the loop is back here, the initial, now I say initial length, and it's not, initial length is how much of, is really the, how much of that edge is still inside of the magnetic field. This is the subtlety about what we mean by an area calculation, because now our area is going to be changing. And so here's the tough thing. The actual physical loop's area doesn't change. How much of that area is in the magnetic field is changing. So your area is how much area, loop area is in the field. It's not just the raw area of the loop necessarily. Okay? If the area is not changing, meaning it's not moving, or its configuration, its size literally isn't changing, then it's just a constant. Otherwise, you have to figure out a function for a changing area, which is what we have here. Okay? So, B and theta are constant. The magnetic field is fixed. Its inclination to the field is fixed. So this means we're going to have our function is a minus b cosine theta, because they're not changing, dA dt. So now we have to figure out what's the area function. Well, just in fixed time, area is just going to be width times depth, okay, in this thing. But as a function of time, well, the width isn't changing, but the depth of the loop inside of the field is, because we are moving this out at some speed, v, pulling the loop out. All right? So what this means is I'll have width, and I start with the initial depth, and then first zeroth law, distance equals rate times time. Change of position equals speed times the change in time. So that product of speed times time is a distance, and it is shortening the depth of that loop. So I know the area of the loop that's still in the field is decreasing because I'm pulling the loop out of the field. And so I can use the speed of the loop coming out of the field as a way to measure how much the depth is at any given time. The width will be constant, but the depth will be changing, therefore the area is changing. So we have our area function. AT will be the width, I should write that more like a W instead of an omega, minus VT. That's the function that we'll have to differentiate. Okay? So, or do derivative of. But we're not done. Well, I guess we could note here that the final time will be equal to the max. Is this 4.8? Yeah. It'll take 3 seconds to pull this out. And at 3 seconds, when there's no more area in the field, there's no more induced voltage. Okay? So any one of those terms goes to 0, and you have no more voltage there. Or you have, so area at the final time here is going to be 0. So just a little, what we expect after 3 seconds, we wouldn't expect anything to happen yet.
Isn't it 1.6 meters per second and the distance is 4.8 centimeters?
Oh no, that's supposed to be centimeters, sorry. See if I can go up and edit this. Thanks for asking. Yeah, that's supposed to be centimeters. That'd be really fast, 1.6 meters per second. We'd still measure something, but be smaller. All right, so we have that going for us. So now what we can do is just finally do the math. So the induced voltage minus B cosine theta, and it's going to be the derivative, time derivative of that area function, which is the width times d naught minus Vt. And this is really nice. It works out to just be the width, speed, magnetic field, cosine theta. And so let's see, 0.031 meters. The speed was 0.016 meters per second. We were given a magnetic field, cosine of 0, and we get basically 36 microvolts. So 36 millionths of a volt, not a lot of voltage, therefore not a lot of current flow, but it's some current flow. All right? So it's just another kind of simple use of those 3 things that we extracted from Faraday's law. All right? So these sorts of things, if I'm real certain it's in the reading, what do these things get used for? Metal detectors, traffic systems. I mean, all these sorts of things are all, when we get into inductance and whatnot, material to all sorts of just sort of sensor arrays and whatnot. Of course, motor action ultimately is the big deal as we move on. All right. That's enough of the examples for just Faraday's law, that particular expansion. Now I want to talk about a thing called motional, not emotional, EMF. And EMF meaning electromotive force. It's a voltage. And so a question we could ask is, what happens when a conducting bar is moved through a magnetic field? And I could say, why ask? And I would just tell you because Faraday said so. Faraday said that a voltage will be induced when you change the magnetic field. And what that means is motion, in one sense, equals a change in the magnetic flux, at least within the context of what we're talking about. If I move a conductor through a magnetic field, I will change the flux and I will induce a voltage. Okay? So, let's kind of step through this conceptually. First, the charged particles in the bar, the conductor, will be subject to a magnetic field. And that magnetic field, or that force rather, the magnetic force is always computed as the cross product of the charge speed and the magnetic field. So we covered this a while back. This was in our setup to the Biot-Savart law. Right-hand rule. So if you go back a little ways, we talk about the right-hand rule. So again, in the direction of speed is your index finger, your middle finger perpendicular to that is the direction of the magnetic field, and your thumb would be the direction that a positively charged particle would go in that scenario. Therefore, a negatively charged particle would go down. Okay? So keep that in mind as we deal with this. 2. So long as motion is not parallel to flux, FB, there will be a non-zero magnetic force on all charged particles. One direction for the plus ones and one direction for the minus ones. Given that the plus charges in a conductor tend to stay fixed, could you have a magnetic field strong enough to rip the protons out of place? Yeah, that's certainly possible, not very likely, and we have other problems once the protons start moving, okay? So we won't worry about that. But the electrons, the free electrons, they will get moving. And now I'm no longer have a charge distribution that's at equilibrium, and I in addition to current flowing, and I now have a voltage set up. Okay? So conduction, electrons are going to move. Which will create a non-zero electric field due to redistribution of charges. Therefore, another force, F equals charge times electric field, is now acting on those electrons. So we're going to draw a picture of this and work through how the equation will shake out in the end. But we need to go through the motions of what's going to happen on the inside and why. So we start off with those electrons getting deflected by the magnetic field, which causes them to move, which causes the creation of this induced voltage electric field, which now introduces a new force to the system. And it's a force that will be opposite the magnetic force. So eventually they will come to equilibrium. Okay? Or there's at least that possibility. So I'm going to need to go to a new screen to draw a pretty picture of this. So these dots are vector arrow tips coming at you. And the reason I did that is because they're easier to draw than vector tails going away from you. All right. So this is going to be the magnetic field coming out of the page at you. And we'll have some bar in this area here. And we'll have it moving through that field with some speed v. That's a terrible arrow tip. There we go. So the bar is in the XY plane of your paper, of the screen here. The magnetic field is coming out of the page / screen at your face. And that means that I can use this right-hand rule to talk about what's the magnetic force on a positively charged particle and then flip it for the electrons because we're concerned about current flow. So this will require some contortion. The only downside of the easy draw of the arrows is that it causes us to twist around. So the magnetic field, you want to point the tip of your middle finger at yourself as opposed to its long side. Okay? So magnetic field pointing at your nose. Twist that over so that your index finger is going to the right, and that means that a positively charged particle would go towards the bottom of the page. Well, a negatively charged particle will go the other way. All right? So, right-hand rule says electrons or magnetic force on the electrons is up. Now the moving electrons will produce an electric field, so the electric force on those electrons is going to be down because it's more positively charged at the bottom of the rod. So the electric force is down. They're going to be opposite one another. One reason to know that, even if you didn't have the right-hand rule telling you that the top end is going to become more negative, which means the bottom end becomes more positive, which means the electric force is towards the bottom. If you recall, we started with EDL equals minus d flux magnetic field D. So they're opposite. mean, you should expect them to be opposite because of the thing we started with says they're opposite. The better reason is what we talked out about how the charge distribution changes. Okay? But you should expect it. You shouldn't be surprised by it, at least consistent with the other stuff that we did. So at equilibrium, we're going to eventually get to the magnetic force equals the electric force, which means QVB equals QE, which means E equals speed times speed of the conductor times the magnetic field in this context. Well, hopefully you recall that voltage, it equaled ED, or in our case EL, length of the rod. Voltage equaling field times distance is just a extension of Coulomb's law. Let's do that for grins here. So remember, Coulomb's law said that you have K, Q per D squared. And if I divide by Q, then I'll get E equals KQ per D squared. And we also have the fact that if I multiply this times D, then that gives me work done per unit charge, which is going to be K Q per D, and this is how we define voltage. So you end up getting voltage as ED out of all of that. So this is just kind of old knowledge. We could have got to that. In fact, we did mention that very briefly in week 1, day 2, when we worked out Coulomb's law. We didn't get to really see it applied until we got to capacitors. And now we get to see it applied one more time in this case. And so, anyways, all of this boils down to the fact that my voltage equation in this case can work out to be, use this funny symbol for induced EMF, would just be the speed of the conductor, strength of the field, and the length of that conductor. Because that voltage is set up over some path length. Remember, we have, we're adding up all of the electric field dot products with the length of that path, the loop or conductor length, and that's equal to the negative time rate of change of the flux that that loop is experiencing. See, I was going to bring it back to the law, even if you're not going to do the vector calculus, blah, 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 at least interpreting that calculus to mean what it means physically. All right, and connect it with some other ideas. So this right here would be a mathematical description of motional EMF. So we started with a statement about motional EMF. I mean, if I drag a conductor through a magnetic field, Faradays' law tells me that it'll put a potential on that because it'll get current flowing, which is backwards than what we normally do. And this would be a mathematical statement of what motional EMF means. Motional electromotive force. All right. We'll give an example of this, of why it's important in technology, then we will take a break. So, space missions like this one, the most expensive goal was to deploy the satellite, okay? But along the way to deploying that satellite, why not take advantage of the chance to do other experiments? So I imagine that in this one, they wanted to simply see how long a tether they could have, what the strength properties of that metal wire was, knowing that it would undergo some electrical interactions. Let's measure that while we're at it, et cetera, et cetera. All right? So we just don't want to just get the hunk of junk up in space. We want to take advantage of the opportunity to get other information for the progress of science. All right? So we always try to layer lots of stuff in there. Oh, the shuttle speed, I guess that's going to be important. Speed of shuttle is 7.6 kilometers per second.
Is that the actual field strength of the Earth, or is it just?
Yes, that is, yeah. And this would be a comparable speed for the space shuttle in orbit, all right? So this is easy. We just get to use the equation. The voltage is going to be the speed times the length of the wire times the field strength. So we do all of that computation, change things to meters. 20 kilometers is 20,000 meters. And then the field strength of the Earth, etc. And we get a voltage of 7,800 volts. Okay? Now, that's a lot of volts for just dragging a metal wire through space, through a magnetic field. But it's also kind of a large speed. Okay? That changes things. And so just a little factoid. Astronauts, whoops. They measured half an amp at 3,500 volts. And the reason they were able to do that is because a complete circuit consisting of the wire and ionized particles, ionized atoms, for the return path. Interesting. Stuff you don't expect. So they got a lot of information out of this. They got, of course, the tether eventually broke, and they expected it to break. Okay, and so they were able to figure out, okay, how much stress and strain did this wire endure before it broke? I imagine they measured its temperature. How did the resistivity of this thing change under these conditions? Because temperature affects resistance. I bet you all those things were going into the pewter while this thing was being reeled out. 20 kilometers. I imagine you can reel out 20 kilometers pretty fast, but you wouldn't want to reel it out too fast because it will snap faster than you want it to, okay? And so the return path. There we go. So this stuff matters. I mean, if you work for NASA or one of the national labs, you're going to do this sort of stuff. And how many pieces of data can we get out of this thing that we think are useful? Okay? And so the physics, you know, stuff you learn in physics courses and chemistry and whatnot, they're going to keep applying all the way through. And what you'll probably realize when you get there, and I hope you all go to grad school, is that much of it was stuff you did as an undergrad. A lot of it will even be stuff you did at this level of physics, chemistry, et cetera, et cetera. And then a lot of it will be at higher levels, granted, right? But you'll spend a fair amount of time noticing that, wow, that was second semester physics or first semester chemistry, you know, and that stuff really does matter in the long run. All right. All right, let's get rolling here. So, wanted to do this problem because I think it has an interesting application to engineering, which I'll share after we work through the problem. But in this case, you have a rod that's on two rails, and so this rod here is being dragged along these two rails, and so what that means is as that rod keeps moving to the right, the area of the loop keeps increasing. Okay, meaning the area through which magnetic flux is flowing keeps increasing because this conducting rod, which is dragging across two conducting rails, is creating a larger and larger loop. Okay, so we're going to continue. We're still thinking in terms of Faraday's law. So, you know, the angle is constant at 0. The magnetic field is constant at half a Tesla. And as area increases as time increases. Because the area increases because the rod's motion always takes time, so I need a time-dependent function for area. So area will be this area that you start with, okay, plus the width, which I called A, little a, times VT. So our area function is initial area plus VT little a, whatever we want. We could have called that width for the bar, length of the bar, whatever we wanted, okay? And so we are going to need dAdt because that's the only thing that's changing. So we're going to be using the form of the equation. Let's see, I should have wrote that here. So induced voltage is going to be minus B cosine theta dAdt. All right. So we need dAdt. So dAdt will just be the ddt of A, which will be the ddt of this function that we just created from scratch, which is just going to be VA. All right. So our function, or our formula, induced voltage, it's easy, just going to be minus, the B will stay around with us, cosine theta 0 is 1, dAdt was VA. And so the voltage that gets induced here will be a minus, you got 5 meters per second for the rod, half a meter for the length of the rod that's dragging along the rails, half a Tesla for that, and you'll get a minus 1.25 volts. Just by dragging this thing at a constant speed across these rails. Now, it's a simple enough problem to solve for. Why in the world would you do it? Well, this is partially like a railgun. You've heard of them, right? Okay? And in a railgun, you have an enormous amount of current that produces an electromagnetic, of course that one we run current in the opposite direction so that it creates a pulse in one direction and launches some hunk of metal to a relativistic speed, and thus creating a plasma ball that goes through lots of steel walls, whatever's in its way. Not quite a railgun in this case, but on its way to being a railgun. But in this case, what in the world might this be useful for? Well, what if you needed to have a mechanical switch that something other than electricity caused your mechanical switch to actuate? So let's go back to space travel. Things are really warm while you're in Earth's atmosphere, and then they get really cold once you leave the atmosphere. Right? So let's say that there's a particular temperature in space that you want something to happen, but you don't want to waste any battery energy on a circuit that's sensing for that location in space or is any other ways using up power. All you would need is to have a couple of rails and a bar that's stuck at the top of the rails. And when that bar shrinks, it slides down the rails in Earth's magnetic field. And as it does that, it produces a voltage, which would allow you to actuate, it could be what allows an on switch to happen. As soon as I get non-zero voltage from this thing, poof, the button is pressed and separation of stages, you name it. Now, I don't think this is the way they separate stages, but, okay? If I needed something that didn't use power, but produced power in order to perform a function, and all I had to do was let a piece of metal fall, that would be a mechanical switch that was actuated by things other than electricity. Okay? Or maybe that bar simply falls down the rail and finishes a conducting path. That's probably riskier than just letting it generate some voltage to open or shut something. Okay? Now, I just made that up. Okay? There's probably a zillion things that you could do with something like this, but it's that kind of something really basic could make a really slick thing. Now, here's the trick is, in this scenario, I would need to pick a material whose thermal properties were of the type that when it reached a particular temperature, which I know that at this range of distances from our surfaces, that's the temperature, and if that's where I want this to happen, then that's where it'll happen. All right?
I can't search.
Every now and then I press this button on this phone or watch. Anyways, so inductance being a proportionality constant, hopefully your book pitches it that way at least once, it is, the flux or a coil is proportional to the current flowing through it. The way I would write that mathematically is that way. N for the number of coils, number of loops in the coil, flux, that thing we've been hitting flux a whole bunch, all right? And that's directly proportional to current. All right, so this idea in mathematical terms. And so inductance, okay, it is the name of this proportionality constant. Describing what we've been talking about, which is the connection between the path for current flow and the flux. Magnetic flux. So we would go from this N theta V is proportional to I to, all right, not theta, N phi B equals Li. Obviously, L is the best letter for inductance. Okay? Which is totally unconfusing since we use L for angular momentum, we use L for length. All right, that's is the convention. Capital L in this context refers to inductance. All right, and so as a proportionality constant, I guess up here, you know, there's some proportionality constant K, and we like to call this proportionality constant, you know, L. So inductance, one way to think about inductance would be the number of flux planes per unit current. You won't find that in a book because I just thought of it. Okay. Because that's what it is, the number of flux planes, because that N refers to coils, number of coils, flux is flux, number of flux planes per unit current. Okay. And they call it a flux linkage. Okay. So flux linkage. You gotta be careful how you say it. Flux. All right. That's the flux linkage is the more conventional term. And just so you know, a unit dimensional analysis, that's what we mean when we put things in these little funny brackets. So if I pay attention to these things here in terms of their units, we like to talk about inductance in terms of henries, which is a physicist named Joseph Henry in the late 1700s is responsible for creating inductance. So the unit for inductance is henries, which is 1 Tesla meter squared per 1 amp. That's what a henry is. So we have Teslas, henries, newtons. Gauss is another measure for magnetic fields. There's all these unit names to track with. All right? So, so we have inductors. Inductors are coils. Okay? Yay. And coils have an inductance value, like resistors have a resistance value, et cetera, et cetera. Now, the weird thing about all of this is that you have self-induction and mutual induction that happens in this context. So let me write some stuff and then we'll try to pay attention to it. So I have this induced voltage formula that says the changing flux per unit time is the negative, or the negative of that is what my voltage is. I can, given what we just saw, instead of theta, and that's not theta, phi b, I can put this n phi b in there. Is everybody okay with why I can do that? I'm summing it up by using that factor. That's all I'm really doing in that case. All right? And we just determined that this n phi b equals inductance times current. So that means that I have the ddt minus ddt of Li, which means that my induced voltage would be equal to minus the inductance times the rate of change of current. Okay? So how current is accelerating or decelerating, if you will, would be a way to pitch a DIDT. Okay? So what does this do? This extends Faraday's law for us to a new context. When I'm dealing with coils and I know their inductance, which they have that value like resistors do, then I can measure the voltage or compute the voltage, predict the voltage with this equation, which is easier than some of the other stuff we've been doing. Area and, all the other stuff. That works if you need to go that direction, but you don't always need to go that direction. This is a way to do that. So that's all short and sweet and nice and good and everything like that. But we just need to acknowledge the fact two coils or inductors. We call them inductors because they do what? They induce voltage if they're in the presence of a magnetic field. Our voltage is induced in them by means of redistribution of charge, otherwise known as current flow. If two coils that are placed close enough to one another will influence one another due to changing magnetic flux. So changing current in one coil leads to flux through another coil, okay? And that means that current will flow and a voltage is induced there. So this self-inductance business, okay, happens within the coil itself. They're kind of self-defeating in one sense of the word. Changing current in one coil will produce a flux through the other coil. However, that current in coil 1 produces an electric field. So it's a self-inducting thing. So when we say self-inductance, we mean what a coil does to itself when it starts to generate a magnetic field. And then mutual inductance is just what we've been paying attention to. We've been paying attention to essentially mutual inductance for this whole lecture so far. But mutual so this whole, both of these things, are wrapped up in this right here.